Hello everyone, continuing on our basic rules of probability. Today we are going to be focusing on a specific scenario of multiplication rules where the events are independent. So let's talk about these independent events. Now we remember in a previous video we talked about multiplication rule, which says that multiplication rule, guys, remember, of probability is given by probability of A intersection B when A and B are two events. So here we are focusing on independent events. That means the events, both these events, do not affect each other. That means if one event has occurred, it is not going to make a change in the assessment of the probability of the occurrence of the second event. So simply these events are independent. So what basically it means is that, take a very simple example, is if I flip a coin. The first time I flip a coin, I might get a head. Okay, second time I flip a coin again. I might get a head or a tail, but the flipping of the second coin is not going to affect the flipping of the first coin. So that's the literal meaning of being events to be independent. Events are not going to affect each other. And the way we define is that if two events are independent, then the probability of A intersection B is given by the product of probability A with probability B. Furthermore, definitions can also be seen as, so here if it is two events are independent, if the probability that A occurs given that B also has occurred is the same as the probability of A. Remember, this is much more simpler to keep in mind, that probability of A intersection B is the same as probability of A and B. Another two forms are that probability of A given that B has already occurred is not going to affect, it is the same as probability of A. Or we can also think in the form is that probability of B given that A has already occurred is not going to affect the probability of B. So this is the same as saying probability of B given A is the same as probability of E. So all these three statements, guys, are equivalent statements, which basically says that the events are independent. Okay, let's look at some of the examples on independent events. We look at an example. We have seen this white and green die a lot. So let's look at the scenario where one event when a white die shows a 2. Let this be event A, and the sum of dice is at most 4. Let this be event B. We would like to know whether these events are independent. So what we first need to know is what is the probability of A and then probability of B. Let's start with this. Okay, what's probability of A? That the white die shows a 2. So looking over here, what's the white die showing a 2? So this is white die showing a 2. So let me highlight that one. This is what we are looking at. So the probability of these events is 6 over 36, which is 1 over 6. Okay, now let's look at that, the probability of event B. The sum of dice is at most 4. At most 4. That what are the probable scenarios? We can have maximum, it can be 4. That means the events can be 1 and 1, 1 and 2, 2 and 1, and 2 and 2. Okay, so we can have either of these 4 cases at most. The sum is, the sum is 4. Yeah, so 1 plus 1, like let's look at this one. 1 plus 1 gives us 2. So here 1 plus 1 is 2. Then we look at 1 plus 2 or 2 plus 1. So 1 plus 2 is 3 or 2 plus 1 is 3 and 2 plus 2. Now these are the two dice being thrown we're looking at. So basically we are looking at these 4 scenarios. Okay, and then we also have another scenario where we can have 3 and 1. We forgot that, remember? 3 and 1 gives us a 4, and 1 and 3 and 3 and 1. So all the scenarios where we are looking at is this. All of them when added gives us the sum to be 4. So 1 and 3 and 3 and 1. Remember 1 plus 3 is 4 and 3 plus 1 is also 4. So how many possible events are there? 1, 2, 3, 4, 5, 6. So the probability of B again is 6 over 36. Okay, so once again it is 1 over 6. We would like to know that, so we have got y and the sum is at most 4. Okay, now we need to know the common part between A and B. So notice, what is the common part? This is the common part. 2 and 1 and 2 and 2. That's only common because that's coming, white die shows a 2. So A intersection B, guys, are the terms which is 2 and 1 and 2 and 2. Okay? Because the white die has to show a 2. Remember, the white die, that's the white die is the first one, these two. So the probability of A intersection B is what? 2 over 36, which is 1 over 18. Okay? Now, let's look at, are these events independent? What is the meaning of independent? Probability of A intersection B should equal probability of A times probability of B. Now what is probability of A? 6 over 36, and probability of B is also 6 over 36. So this basically is 1 over 6 times 1 over 6, which is 1 over 36. Whereas A intersection B is what? 1 over 18. Now, can 1 over 18 be the same as 1 over 36? Nope. So, what does that mean? That's not possible. So, these events are not independent. The answer is no. Okay. Moving further. How about that a white die is even and a white die is 5? So this is going to be, we'll like to know what about the independence of these events, A and B. Now when I say white die is even, so what is the probability of A? All these, there are 18 of them, guys. So it's 18 over 36, which is 1 over 2. What about probability of B? That the white die is a 5. So white die is a 5. It's this one. Let me highlight it. The white die is a 5. Okay, so what do we get the probability of B, guys, to be? We get it to be 6 over 36, which is 1 over 6. Now, do they have anything in common? Let's look at probability of A. Let me highlight it with a different marker. So let's use the pink here. Remember, that's the white die is an even. Okay. Because if you look at the intersection, the 2's here, the 4's here, and the 6 here. Okay. That's this probability of A for us. And this is probability of B. Do they have anything in common? They have nothing in common. So we see A intersection B is 0. That means probability of A intersection B is 0, which definitely is not equal to probability of A times probability of B. And what is that value? It is 1 over 2 times 1 over 6, which is 1 over 12. So clearly, we see that these example here, this is the probability, this is not independent. And also notice, even though it is not independent, but the probability being 0, which we talked in the previous session, shows that these events are mutually exclusive. So very important, independence and disjointness are not the same. Keep this little thing in mind. Okay, so we have had an example where in the previous one where we found that the events were not independent. Here we found, again, the events are not independent, but they're also not, they are disjoint here though. Now let's look at an example where the events are independent. So let's start with this one. It says, when we draw one card from a standard deck of 52, okay, are the events that the card is an ace. So card is an ace, let that be an event A. And the card is a spade, be an event B. We like to know whether they're independent. So first thing is, what is the probability that the card is an ace? There are 4 aces out of 52. So 4 over 52, 1 over 13. Now a card is a spade. There are 13 of them. So 13 over 52, which is 1 over 4. What's the common between this? A card is an ace and a card is a spade. There's only one event. Okay, so what is the probability of A intersection B? Just 1 over 52. Now let's see whether these events are independent. Probability of A intersection B, is it the same as probability of A times probability of B? So this one is 1 over 52. The right hand side is 1 over 13 times 1 over 4, which is also equal to 1 over 52. And yes, the events are independent. Now let's look at another example. Here we are going to flip a balanced coin 3 times and they're independent. Let A denote that the first flip is ahead, B that the second flip is ahead, and C that the first 2 flips are ahead. So remember, when we flip a coin 3 times and it's a balanced coin, if you remember from creating a tree diagram, just to give you a heads on here, so when you first have a flip, either it can be what? A head or a tail. Then once again, the second flip can be either a head or a tail. If the first flip is a tail, we'll have a head or a tail. Then the third flip, again, there are going to be 2 possibilities. The same goes here for each one of them. So if you want to find the sample space, what are we going to do? We're going to say, oh, the first sample space, if we go by this branch, is H, 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 and that's how we go. Okay, let's look at, we want to say the A, what are the elements which come in this? The first flip is a head. First flip is a head. This is a head, this is a head, this is a head, head. So how many elements? 4. Total elements, 8. So what is the probability? 4 over 8, which is a half. Okay, now let's look at what is the probability of B. It says the second flip is ahead. It doesn't matter what is the first or the third, it's the second flip is ahead. So we have this one, the first is second, and then we have THH and THT. So that's the second. So there are again 4 elements. So again, the probability is 4 over 8, which is a half. Now, what is the probability of C? C is that the first two flips are ahead. Okay, let's look at a different marker here. Okay, we'll take this. So C is first two flips are ahead. So I will have this time first two, this one, H and H. So there are only two terms. So what is the probability? 2 over 8, which is 1 over 4. Now we'd like to know whether the events A and B are independent. So the first thing we need to know is, what is the probability of A intersection B? Okay, to look at this one, let's look at the red markers here and the blue check marks. So what's common? The common is HHH and HHT. So that's common. So what is the probability of A intersection B? Is simply 2 over 8, 1 over 4. Okay, let's look at what is probability of A times probability of B, which is half times a half, which is again 1/4. So what is the answer? Yes, remember, how do we say that these, if the probability says independent, what does that mean? Probability of A intersection B should equal probability of A times probability of B. In our scenario, it is correct. So the answer is a yes. Let's look at A and C. First of all, we have to find probability of A intersection C. Now A intersection C. So remember these two. So again, it is 2. So the green markers and the red markers. So there are only two common. So it is again 2 over 8 and the 1 over 4. So in order to say if it is independent, what we need to know, A intersection C equals probability of A times probability of C. So A intersection C is this. Let's look at probability of A, which is a half. Probability of C, 1/4. What is the probability? 1/8. Clearly, 1/4 and 1/8, they're not the same. So here the answer is a no. Okay, let's look at some more examples of different forms here. Now here we are given a probability of an event A to be 0.2, probability of an event B to be 0.8. And we are given that these events are independent. So if the events are independent, what does that mean? Probability of A intersection B is nothing but probability of A times probability of B, which is probability of A, 0.2 times 0.8, which is 0.16. Now remember, probability of A union B, this is our general addition rule. It is probability of A plus probability of B minus probability A intersection B. Now what's probability of A? Given to us 0.2 plus 0.8 minus 0.16 from the first question. What do we get? 1 minus 0.16, which is 0.84. Let's look at some other concepts in independent events here. Now, when we draw cards, so what happens is when we draw a card and we replace it, then we don't have issues. But if we take a card and we do not replace it, then definitely it's going to have an effect on our probabilities. So the process where we sometimes replace back the element or sometimes we do not replace back the element is called sampling with or without replacements. Let's look at an example related to this. Now we're going to select 3 cards from a standard deck of cards. First event is that the first card is a heart. H2 is the event that the second card is a heart. And H3 is the event that the third card is a heart. So that means you're drawing 1 card at a time. Now we'd like to find the probability of getting a third heart when the first 2 cards drawn were hearts also for those cases. So what we want to find the probability of the third heart. Okay, so we want to set third heart, or the probability of drawing the third card. Let's say this way. So the probability of drawing a third card of heart. Now, sampling with replacement. So just think logically. If you take a first card and it is a heart, you replace back. How many cards you have left? Again, 52. So second time you take a card and then you put it back, again you have 52. And again you have 13 hearts. So the probability of getting a third card of heart when every card you draw earlier have been replaced is nothing but 13 over 52, which is 1 over 4. Now let's look at this one, sampling without, this is the key, without replacement. And we'd like to find the probability of drawing a third card of heart. Now, let's look at it. When we draw the first card, and it is a heart, remember that's what the question is saying. So we do not replace it. So how many cards are left? We are left with 51. And because it was a heart which was being replaced, so how many hearts are left? 3 hearts are left. Okay. Now, so 11, we have 51 cards, and we are having now, hearts. 1 heart has been replaced, so we are now only having 11 hearts. Now let's look at the second card again is drawn, and that happens to be a heart. And we do not replace it back. So how many total cards are there? 50. And now, I made a mistake. So the first time we draw a heart, we had 12 hearts left. And now when we draw the second time, we have 11 hearts left. And the total number of cards are 50. So the probability of getting a third card of heart is now 11 over 50. Remember, without replacement means every time you pick up a card, you do not put it back. And on top of that, we are given the condition that the first 2 cards we drew were hearts for those cases. So the first time, when you do not replace, you are left with 51 and 12 hearts. And then when you take the second card, again, you don't replace back. Now you're left with 50 total cards and 11 hearts. So the probability that the third card is of heart is 11 over 50. Thank you.